Hello and welcome to lecture 13. So we're going to be talking about implicit differentiation. So what is this about? Well, there are many things in nature that we'd like to describe with the language of math that we cannot do with just the graph of a function from the x-axis. So the graph of a function from the x-axis has this property, of course, that every x, there is just one f of x, right? That's the defining property. If we don't have that, we simply can't define the function. But they are easy to come up with examples of curves that we'd like to describe, but we can't do this with a graph. So an easy example is a circle, right? The circle cannot be described just as the graph of one function, because for every possible x we might be interested in, there are two values here and here. But you can trivially come up with a huge infinity of different things, different one-dimensional curves that you cannot describe as a graph. Okay? But we'd like, nevertheless, to be able to apply these tools that we're learning. We'd like to be able to apply the tools of calculus to understand things about curves like this. And particularly, we'd like to be able to find the tangent line, find the slope locally of this curve, find even the second derivative. Okay? And the kind of curves we're interested in will be defined as equations of x and y. So in the case of the circle, it's pretty easy. It is x squared plus y squared equals r squared. Well, I say it's pretty easy. It's pretty easy if you have seen it already. So why is this the correct thing? Well, let us draw a little triangle like this. Okay? And let's suppose this is a point x, y on the circle. Then this side of the triangle has got length x, this side has got length y. So then the hypotenuse by Pythagoras will be the square root of x squared plus y squared, right? So if it satisfies this equation, it'll exactly say that the length of the hypotenuse is r, right? So if we talk about all the points x and y, for which this is true, for which this distance is r, that's exactly the set of points of distance r away from the center. That's why this thing describes the circle. Okay? So many of you perhaps have seen the equation for the circle. Maybe this was too fast. Go over this, think about this, convince yourself that this just follows from Pythagoras' theorem. Okay? All right. So that's an example of a set of points we'd like to understand, we'd like to apply the tools of calculus to, but we cannot if we just work with graphs. Well, strictly speaking, we could, but it would be harder work. So let's see what happens if we try and write this thing as the graph of a function. So let's try and solve, because this is kind of indicative of why what we're about to talk about works. So let's try and solve this equation, star, for y. What happens? Well, we're going to have y squared is equal to square one type at a time. Y squared will be equal to r squared minus x squared. And then if we want to find y, it'll actually be plus or minus the square root of r squared minus x squared. Right? Because if we have minus the square root of this and square it, we still satisfy this. So there are actually two solutions. So that gives us kind of the way to go. We could define y1 of x to be square root of r squared minus x squared, and y2 to be minus the square root of r squared minus x squared. And that would give us the top and the bottom of the circle. So this is y1, this top part here. And let's try and get a different color. don't have a different color. And this part here is y2. Okay? Because this is the positive and this is the negative. So if we did that, we can describe the circle as two graphs. You know? It can't be done as one, but it can be done as two. So we could get around these problems by just breaking up any curve we have in the plane into individual graphs of different functions. However, that means finding them. And in this case, it's not hard, but in the more general cases, it's really hard, and that's not the efficient way to do things. So we're going to develop a machine that allows us to do the kind of things we want to do without this kind of thing, without breaking things up into graphs. Okay? So let's think about the kind of curves we'll be talking about. Let's, for example, consider a curve like this, which we're going to analyze later anyway. X to the 3, y to the 3 equals 6xy. This too will form a one-dimensional curve inside the plane. And it's not one we're going to be able to understand or plot very easily at this point. But we're still going to be able to do some calculus with it. Now why do we know it's one-dimensional curve? Well, think about the fact that the set of all x and y in the plane is a two-dimensional set, right? So x comma y for all x, y is 2D, right? And if we have an equation like this, then we are relating x to y. We are constraining the degrees of freedom. We've removed one degree of freedom. Here there are 2 degrees of freedom. X and y can move as any way we want. Here they are related. We've removed 1 degree of freedom. So we've removed one dimension. We've gone from something which is 2-dimensional to something which is 1-dimensional. All the x and y that satisfy this will be a 1-dimensional curve, just like this is a 1-dimensional curve. Okay? Cool. All right, so this is another kind of example we're going to do. All right, now let's do an example of this kind of stuff and just see how it goes. Okay, let's do it this way. So, example. Find the tangent line, I'll just call it T line, to x squared plus y squared equals 25 at 3, 4. Okay. Solution. First step, let's check that this point is actually on the curve. So 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. This is definitely on the curve. Yeah? And as we know, this is a circle. It's a circle of radius 1. We already have a circle up here. Let's clear off some details and use the same picture. So this is our guy, the radius is 5. And we are trying to find the tangent point at, or the tangent line at 3, 4. So this is 3, let's say this is 4. So it's kind of like this. It's a point like this. So trying to find the tangent line, so it's going to look like this. Right? It'll be sloping down like this. The best picture, but you know what I'm trying to do. Okay, so this is how we start this. We are going to pretend y is a function of x. So I've just spent the last 5 minutes telling you that y cannot be a function of x. We are going to pretend it is, because it turns out for what we're going to do, we're going to get away with it. We are going to assume this thing which is false, do some calculations, get an answer, and we will get the right answer despite the fact we made a false assumption, right? Which is a little bit of a a strange thing to do, perhaps a little bit of a sneaky way to solve a problem. But there's a real reason we get away with it, and it's not even a difficult reason. And the reason is because locally, these curves actually are the graphs of functions. So locally, around some particular point of your choice on the circle, it is indeed the graph of a function. So this point we're interested in, which is 3, 4, it is indeed the graph of a function. It is the graph of y1, right? So since taking the derivative is a local thing, it just cares about where we are around that point, we can get away with the assumption that y is a function of x, even though it's not, because it's not globally, it's not true everywhere, but it is true around the little piece of our one-dimensional curve, right? But we're not going to specify that. We're just going to make this broadly false assumption, work with it, get the right answer out, okay? But I always feel a bit uncomfortable with this because I don't want you to think this. I don't want you to walk away or to finish this section or this video with some totally false thing, which is why I do the build-up about curves not necessarily being graphs. So I like to write the words, let's pretend y is a function of x before writing y as a function of x, okay? Just to remind myself and just for you to remind yourselves that it's not actually true. It's just a simplifying assumption that we get away with. So if you're doing a free response, please write those words. In fact, when you work this out on paper, as I hope you do, when you're doing your own work, write the words, let's pretend. Get in the habit of doing this so you don't learn implicitly some false thing that's later going to confuse you. Okay, math is cumulative. If you get some false idea, then later down the road, it's going to come back and bite you hard. So we don't want to do that. We want to build on a solid foundation. We know that curves like this, curves defined like this as a function of x and y, aren't the graph of some particular function. Y isn't a function of x, but we're pretending it is. All right, let's pretend. Then, so let me underline this because it's pretty important. Then, replace y with y of x in the equation. So then we're going to get x squared plus y of x squared equals 25. And then we differentiate it. And if we differentiate this, differentiating with respect to x of x squared is easy, it's 2x. Here, I'm going to have to apply the chain rule, right, which is what we just learned. So another thing to say is after you watch one of the videos, please go to the practice problems, do some practice problems, make sure you've understood this. It can seem very convincing when you watch me do it, but make sure you're comfortable with it yourself so that when I do these calculations, when I do these steps in the following lecture, it doesn't seem mysterious to you. So you'll get much more out of each video, each in-person class, if you are solid with the stuff that's happened before. So practice it. Please practice it. Yeah? So we can differentiate this guy. And the chain rule, the outer function is x squared, the inner function is y, right? So we differentiate the outer function to get 2x and apply the inner function to it. So we're going to have 2 y of x times the derivative of the inner function. The inner function is y of x. Its derivative is y prime of x. Right? Then we differentiate 25 with respect to x, which is just 0. Cool. Having done that, we now have just a function. We have an equation which involves y prime, y of x, and x, and we want to solve for y prime. So solve for y prime of x. If we do this, what do we get? We get that y prime of x is equal to minus x over y of x. Having done this, having done all the differentiation, we now no longer need to write y prime of x. We can now just write y prime. So finally, y prime equals minus x over y of x. Sorry, minus x over y, because we're not writing y of x anymore. All right, key point. It's very tempting when you've done a couple of these questions to stop writing y of x, because it's just extra stuff to write, and you'll see later it gets lengthy to keep writing y of x. However, that's the main mistake that I see happening when I grade these kind of questions. Because if you don't write y of x, then you can easily miss one of the y's to differentiate. If you write y of x throughout, then you're not going to miss it, and then you'll have all the terms. I've done this, every time I teach this stuff, I practice it obviously beforehand. And even for myself, I write y of x because I know that I will easily miss one of the things I have to differentiate unless I replace every y with y of x. And I've done more implicit differentiation than probably anybody watching this will ever have to do in their life, right? So if I know that I'm not able to do this correctly without writing y of x, after all these years of doing it, decades of doing it even, then probably you can't. So don't skip this writing y of x. Write y of x all the way through until you have whatever you're looking for, the y prime of x. Later we'll do the second derivative, y double prime of x. When you have the answer, then no more need to do it. Or when you've done the final differentiation, no more need to do it. But until then, keep writing y of x. All right, so we are here. That should be a key step, right? Because we're looking to find the tangent line. The key point is the slope. We have the point here, 3, 4, right? So at 3, 4 equals xy, i.e. x equals 3, y equals 4. We can just plug in the values. We're going to have that y prime is going to equal to minus 3 over 4. Now in this particular case, we can actually check whether or not this makes sense, because this picture is messy as hell. Let me perhaps move part of it down. So let's zoom in around this part. So I'm blowing up this part over here. Okay. What do I have? I have something like this, and circle it like this. Right? And we're at 3, 4. So say this is 3 and this is 4. So we are here, 3, 4. If we draw the line from 0 to 3, 4, okay, then the tangent line is like this, right? So the tangent line in particular is perpendicular to the line we've drawn from 0 to 3, 4. So if we ask ourselves, what's the slope of this line from 0 to 3, 4? Well, let's see. So we go along by 3 and we go up by 4. So the slope of this line is, again, we go along by 3, we go up by 4. So it's going to be 4 over 3. Yeah? But this line here is perpendicular, and we learned how to calculate the slope of a line that's perpendicular to the line whose slope we know already, right? So that was this stuff of having some triangle that represents the slope where this was A and this was B. And if we wanted to find the slope that is perpendicular to the hypotenuse, right, we create another triangle of the same size. Yeah? And we see that then this has to be B, and then this has to be A. So the slope here is B over A, how far up and down we go, divided by how far along. And the slope here is, we're going along by B, but we're going down by A. So this slope is minus A over B. Okay. So we discussed this already when we talked about normal lines. Review this if it seems unfamiliar to you. Do not memorize things. Do not memorize that the slope of the normal line is minus A over B if the slope of the line we're interested in is B. Start again. Don't memorize that if we are looking for the slope of the normal line of some line which has slope B over A, then it's minus A over B. Don't memorize formulae. Draw pictures. Draw pictures to convince yourself of formulae, and then you're allowed to use them, but don't memorize things that you can't explain. If you find yourself with something you know but you can't explain why, that's the wrong path, particularly if you're interested to do this, to really learn this stuff and to learn the contents of your degree well, that's the wrong path. You don't, or at least for maths, you don't want to know stuff that you can't explain, okay? So if you have a good enough memory to know things, then for sure your brain is good enough to understand it as well. So just spend a few minutes with the explanation and be sure about it. All right, back to this. So we know this guy has slope 4 over 3. So by this thing, we know that the slope of this thing has to be minus the inverse of this, right? 3 over 4. Yeah? So in this particular case, we can just figure it out from the pictures. But let's see what the calculus has told us. Exactly the same thing, right? We have exactly the same answer. So we know this procedure works. It gives us the right answer. Yeah? We made the false assumption, but we got away with it. It gives us the right answer, and it always will give us the right answer because finding the slope is just a purely local thing, and our false assumption is actually true locally. All right, cool. So let's do another example. Oh, and we're not quite done. Find the tangent line. All I've done is find the slope. Okay. If this was an exam question, that would be a classic mistake. That do some part of it and then think and be happy with it because it's clearly the right answer. But we're not wrong. Sorry, we're not complete. We're not done. So that's the slope. But for the tangent line, okay, we know well how to write down a t-line, right? So tangent line, we're going to put the slope, which we know, minus 3 over 4, then x minus the x-coordinate we're going through. And the x-coordinate we're going through is 3. So x minus 3 plus the y-coordinate, which is 4. So this is minus 3 over 4 x, and that'll be minus 3 divided by 4, so that'll be plus 9 over 4, and this is 4, so that's 16 over 4. So that's, putting stuff together, that's 25 over 4. Yeah? And that's the t-line. All right, now we're done. Let's do another example. Find the t-line of this equation, x to the 3, y to the 3 equals 6xy at 3, 3. And find y prime. Okay. Well, first we're going to find y prime. So we don't have the technology yet to sketch this thing. So, well, we know it's a one-dimensional curve. Let's at least check, though, that this is a point on the curve. So let's do some arithmetic. So we have 3 to the 3, so that's 3 times 3 squared, so that's 3 times 9. Also 3 times 9 here. This here is 3 times 3 again, times 6. So we're going to have 3 times 9 plus 3 times 9 equals 6 times 9, which makes sense because 3 plus 3 is 6. So we agree that we have a point. This is a point on the curve. Good idea to do this because it's very easy to miswrite down the actual equation, and this is a little check. You don't do this. All right, cool. So then the procedure is the same. Let's pretend y is a function of x. And then we write the thing as a function of x. So we're going to have x to the 3 plus y of x to the 3 equals 6x y of x. Now we differentiate through. If we do, looks like we are not going to have space for that. So we're going to erase the board, and then we're going to complete this question. What did we get to? So we had x to the 3, y of x to the 3 is equal to 6x y of x. And we're going to differentiate through. So we're going to have 3x squared plus 3 y of x squared y prime of x. And then differentiate this thing. It's the product rule. We're going to differentiate the first term, leave the second alone. Plus leave the first alone, differentiate the second. And then we're going to solve for y prime. So we divide through by 3 straight away, and then put all the y primes on one side. So we are going to have y of x squared, y prime of x, minus 2x y prime of x, and the other stuff on the other side equals 2 y of x minus x squared. So I've divided by 3 as well. And then we're going to factor for y prime. And now that I've done this differentiation, I'm not going to differentiate again. So now you're permitted to stop writing y of x. Once you're completely done with the differentiation, you're sure you're done with the differentiation, now you can just write y prime and y. So we're going to have y squared minus 2x is equal to 2y minus x squared. So y prime is equal to 2y minus x squared over y squared minus 2x. Cool. So at x, y is equal to 3, 3. Plug that directly in. Y prime. So we're going to have 6 minus 9 over 9 minus 6. So the top line's minus the bottom line. So I know this is minus 1. And that's it. So we know that the slope is -1. Cool. So the t-line is t of x is equal to -1, x minus the x-coordinate, which is 3, plus the y-coordinate, which is also 3. So it's -x plus 6. And that's it. That's our problem done. Excellent. Okay, so let's do another problem. So sometimes we want to actually find the second derivative of y for some implicitly defined y from an equation, okay? And that's what we're going to do, and it's going to follow the same procedure. We're going to pretend y is a function of x, and then we're going to solve to get y prime, but then we're going to keep working, going to have to differentiate again to get y double prime, but we're having to work even a bit longer because we finally want the answer just in terms of x and y. So here is the next example. So we're going to have x to the 4 plus y to the 4 equals, I think it's 16. Doesn't really matter, but let's check. Yep. Equals 16. Okay. Find y double prime. All right. Solution. Let's pretend. So write this all the time. Y is a function of x. And then we have x to the 4 plus y of x to the 4 is equal to 16. Differentiate with respect to x. Then we're going to have 4x to the 3 plus 4 y of x to the 3 y prime of x, and then differentiating 16 with respect to x, we just get 0. Solve for x. Sorry, solve for y prime. We solve for y prime, we have that y prime. We can divide by 4 straight away, and we're going to have the y prime is just going to be minus x to the 3 over y of x to the power 3. So we are not done with the differentiation at all, because we're doing the second derivative. So we are not going to replace y of x with y yet. Okay. Right. So we have an expression for y prime, but we need the second derivative, so we're going to have to differentiate again. Diff again. And if we differentiate this again, this is the quotient of this function x to the 3, or minus x to the 3, with y of x to the power 3. So differentiate again, we're going to have y double prime of x is d by dx of this stuff, right? Of minus x to the 3 over y of x to the power 3. Cool. Then we do this differentiation. So everything over the bottom guy squared. So y of x to the power 6. Differentiate the top, leave the bottom alone. Let's just pull out a minus straight away. So we're going to have 3x squared y of x to the 3. Yeah? We've differentiated the top, we leave the bottom alone. Minus, leave the top alone. Okay, we've already pulled out the minus. So leave the top alone, x to the 3, differentiate the bottom, 3 y of x squared y prime of x. Excellent. And now we've done all the differentiation. right? We've done all the differentiation. So now we are allowed to write this just as a function of x and y, which is good because this looks really messy. Let's pull out a 3 as well. So we have a minus 3 x squared y to the 3 minus, minus x to the 3 y squared y prime over y to the 6. Yeah? But we need this just in terms of x and y. So we can't have a y prime there, but happily we have the formula for y prime. It's right here. So y prime is minus x to the 3 over y to the 3. So we can replace that in here. Minus 3 x squared, this thing, minus x to this thing, and now replacing y prime right in there. Minus x to the 3 over y to the 3. Cool. Y to the 6. All right, let's clean that up. So, what powers do we have going on here? We have x to the 3, so we're going to have powers of x to the 6, and then y to the 2, and this is y to the minus 3, so we have y to the minus 1 here. So we're going to put in all the steps carefully. The minus minus now becomes a plus, so we're going to have x to the 6, and then y to the minus 1. All right? Over y to the 6. Now, I don't like this y to the minus 1 because I actually just want positive powers here on the numerator. So I'm going to bring this guy down here because x to the 6, y to the minus 1 divided by y to the 6 is x to the 6 over y to the 7, right? But to have the same denominator, I'm going to have to increase the power here from 3 to 4. Right? So what I mean is I can write this as x squared y to the 4 plus x to the 6 over y to the 7. Yeah, because this thing here is just this thing here, and this thing here is just this thing here. Right? Because we've just increased the power on the top and bottom of y by 1. Yeah? It's y to the 4 here and y to the 7, and it's the same thing. Yeah? And then let's factor out an x squared, so minus 3 x squared, and we're going to have y to the 4 plus x to the 4 over y to the 7. Cool, and that looks kind of like as far as you can go in terms of simplification, but you can actually go just a little bit further because this y to the 4x to the 4 is actually our defining equation for the x and y. So all of this stuff is happening on the x and y that live on this curve, right? Defined by x to the 4 plus y to the 4 is 16. So since this x and y that we're talking about lives on this curve, this particular part of the expression we can just replace by 16. So this thing is minus 3 times 16, which is minus 48 x squared over y to the 7. Cool, and that's it. So this is perhaps harder algebra than we normally do. And this course is not about testing your algebra. You should come here with that already learned. But sometimes calculations just get lengthy. And this is one of these examples. You won't have, most likely, a question as tricky as that to do on the exam, particularly because we're doing online exams. You have to type this stuff in, and that's a pain. So, but you should be able to do it. You should be able to get this, right? So the thing we did was the same procedure. We had this guy. We said, okay, let's pretend y is a function of x. We differentiated through. Then we got something that involved y prime. And we're not happy with that. We actually want it just in terms of x and y. So replace y prime with its formula. Then we have something just in terms of x and y, but we have to do algebra to simplify it. And there you go. If you're doing a free response and you don't and it asks you to simplify and you don't simplify enough, you'll lose a few points. But that's not the biggest deal. And if you are doing a free response and you make some algebraic mistake, but what you do from that point on is consistent, again, you don't lose so many points. So again, we're not testing algebra. Don't be intimidated if this looks very complicated. It's just algebra. You know this stuff. The important point to learn is the setup, as the basic principle of pretending y is a function of x and then differentiating. All right, so that's it for implicit differentiation. So I feel like when I was asking my classes today, some people have seen this before to some extent. Plenty of people haven't. If you haven't, don't be intimidated. This might look complicated, but it's not. It's not complicated, it's just lengthy. Yeah, just practice this and be sure you understand why what we're doing. But this is not a difficult topic. And this has some pretty cool applications. So what this stuff allows us to do is to calculate the derivatives of inverse exponential functions, which are log functions, and the derivatives of inverse trig functions. Okay, so we talked a little about inverse trig functions because we worked out the inverse of the inverse of tan, which was arctan. Just as a warm-up for what we're going to use this for, let's talk about getting the inverse to the exponential function, which is the log function, and being able to graph it. Okay, so the inverse to e to the x. So this procedure for figuring out roughly the inverse is one you can use all the time. So firstly, we know what e to the x looks like. All right, it's the fastest growing elementary function. When x equals 0, it's at 1, and then it grows like crazy, crazy fast, right? And it also decays crazy, crazy fast. This is the exponential function. This is e to the x. Okay, and let's put down roughly the properties of what it does. So what do we know about e to the x? Well, as x goes to infinity, e to the x goes to infinity. In fact, it goes very fast to infinity, right? So we're going to, as a shorthand, write this. E to the x sends infinity to infinity. What we mean is it sends numbers going towards infinity. We don't actually mean we're going to plug infinity into this. Do not treat infinity like a number. Don't put it inside functions. This is just shorthand. Now we know what this actually is. It's the limit. The limit as x goes to infinity is infinity. But I'm just writing this in a more crude way. All right, so it definitely sends infinity to infinity in that sense, in the sense of limit. What else does it do? It sends 0 to 1, right? So it sends 0 to 1. As we go towards negative infinity, it goes towards 0. So negative infinity goes towards 0. And what else does it do? Every value of e to the x is positive, right? So it's sending the entire real line to the positive real numbers. So let's put some notation here, which probably many of you have not seen. So this thing is all numbers, the entire real line. And this thing is all positive numbers. Okay, this is just some convenient language to, instead of writing all numbers and all positive numbers, we just use this symbol and this symbol. Nothing deep here, just a convenient symbol. All right, so e to the x sends all the numbers, the whole real line, and it sends it to all the positive numbers. As we go from minus infinity to infinity, then e to the x goes from 0 to infinity, which is all positive numbers. Okay, so log of x is the inverse of e to the x. So whatever e to the x is doing, log of x unwraps it, right? Think of this as a machine. So we take x, plug it into the e to the x machine, we get out a product, right? An e to the x. Now, log of x can unwrap that, right? We take that thing, e to the x, apply log to it, we go back to x, right? So, since e to the x sends infinity to infinity, log also has to send infinity to infinity. Yeah, so it sends it in a completely different way though, because this guy is sending x to infinity at an incredibly fast rate. So to unwrap that, to do the reverse of that, we have to send x to infinity at an incredibly slow rate. Right? Incredibly slowly goes to infinity. It also unwraps this thing, so it's going to send 1 to 0. It's going to unwrap this thing, it's going to send 0 to minus infinity, and it unwraps this thing, it's only going to be defined on the positive real numbers, and it's going to send the positive real numbers to the whole real line. Yeah. Whatever this guy's doing the unwrapping of it. It's reversing it. All right, now let's try and figure out what log looks like. So most of you hopefully know what log looks like, but I claim we can work it out, or at least get a good idea what it looks like from these basic things. So it's growing slowly towards infinity as we go towards infinity, so it's kind of going like this. As we go towards 0, it goes towards negative infinity, so there's this vertical asymptote like this. At 1, it's 0, so it's crossing like this, right? And yeah, and we just put it together. Let's put these pieces together. It's doing something like this. So this is the graph of log. Cool. Now, if instead of e to the x we did b to the x, it would have a very similar property, right? And the inverse of b to the x will be log to the base b. So inverse of b to the x is log base b of x. That's all it is. All it is. Okay. Cool. And all those properties, e to the x satisfies, b to the x satisfies, and log to the base b also satisfies. But b to the x will either be growing a bit faster or a bit slower. If b is bigger than e, it'll be growing faster. If b is less than e, it'll be growing slower. But basic properties are the same, and it still grows incredibly fast. And same thing for his. So we are going to be able to understand better what the graph of the inverse log is, because we're going to be able to differentiate and find explicitly the derivative of, I think I said inverse log, I didn't mean that. We're going to be able to understand better what the graph of log is, because we're going to be able to differentiate it and find the derivative using implicit differentiation, using what we know about differentiating e. Yeah? And the same for log to the base b. So we'll have a better, more accurate graph than this. And we'll also do this for trig functions. And the moral of this little part, though, is that, so I've said many times in class and in video that we have just a handful of elementary functions that we make everything else out of, right? 1,000 at most. And you need to have a good picture of their graphs. Yeah? And I don't mean memorize them, I don't mean type them into Wolfram Alpha and look at what you see and memorize that picture. I mean being able to figure them out from what you know about them, like we did for e to the x, and now like what we've done for log. So the fastest, most efficient way to do this stuff, to learn calc, is to be really solid on the fundamentals. This is a fundamental. If you are hazy about the graph of some elementary function, go through something like this to figure it out. And with this kind of stuff, you can figure out the inverse of a function if you know the function itself. And please spend half an hour or an hour doing that, closing any gaps you have. That will save you many, many hours going forward. All right, that's it for today. Have a great day.